I'm not offended if people are like, how long until the class is done? It's a hard class. There's no question about it. So, we've talked about, when last we left our heroes, we were talking about the heart's activity as a pump, and we went over the Wigger's diagram and its relationship to the cardiac cycle and ECG and all of that stuff, and it built all together into this talk about how you see it all together as a pump, the Wigger's diagram being the summary of that. I've had a few people share with me their attempts at Wigger's diagrams, and those are good. I'll be happy to give feedback on them. It's a good idea to draw it over and over again and check until you know that you are doing it right. So today, we're going to finally leave the heart and move out into the rest of the body. We're going to be talking about the blood vessels that blood travels through. Now, to begin with, we generally divide blood vessels into 5 main groups. And named in the order in which you find them after you leave the ventricles, you find arteries, which go into smaller arteries, and then you go into arterioles. The arterioles split up into smaller vessels until you finally get to the point of being in capillaries, which are the smallest kind of vessel. Capillaries are extremely numerous. Basically, almost all cells in your body have to be within about 1/10 of a millimeter of a capillary. So there are capillaries everywhere. They are microscopically small vessels. After the capillaries, the vessels start coming back together into larger vessels on their way back to the heart. So after capillaries, you end up with venules. And then finally, those assemble into larger venules and then into veins. The veins get bigger and bigger until finally you come back to the heart, either on the venae cavae, if you're coming back to the right atrium, or the pulmonary veins, if you're coming back to the left atrium. So what we're going to do is go through each of those and talk about how they are different from each other. The main difference is in the structure of their walls. What kind of tissue you find in their walls, how much of it, and so on. So let's see if I have enough colors for this. So let's start with arteries. Now, for all of these vessels, the innermost layer of the vessel, which I will draw in blue, is endothelium. You've heard that word before. That was the word we used when we talked about in blood clotting. It's the innermost layer of cells that secreted prostacyclins, which help the platelets stay quiet. Help stop blood clotting from happening when it should. Just outside of the endothelium, in arteries, is a layer that we will call elastic tissue. Now, when we talked about coagulation, what was the layer of protein fibers just outside of the endothelium? You remember the name? Those are the cells that maintain them. The basal lamina is what I'm thinking of. We said the basal lamina is largely made of collagen. There's also another protein called elastin that you find in basal lamina. This, here in arteries, when I talk about elastic tissue, it's not really different than the basal lamina. It's just that in arteries, the basal lamina has so much elastin in it that it's thick enough to kind of form its own distinctive layer. So we'll call that layer of largely the protein elastin, the elastic tissue layer. Elastin is a protein which is very stretchy and springy. Outside of that elastic tissue layer, we have a relatively thick layer of smooth muscle. Arteries are particularly noteworthy for this. They have a especially substantial layer of smooth muscle. This smooth muscle is largely under the control of the autonomic nervous system, and it tends to apply a little bit of pressure to the blood in the arteries by constricting a little bit. finally, outside of the smooth muscle, there is a tough layer of fibrous tissue. This will have a lot of collagen in it, some other stuff. It's kind of a leathery outer layer. Tough, a little bit stretchy. Mostly it holds the artery together and protects it from damage. These layers make some sense if you consider what the arteries are doing. The arteries are the first vessels to receive blood from the heart, and especially on the systemic side, that means that blood is under a great deal of pressure. The ventricles applying pressure to that blood push that blood out of the arteries under a lot of pressure, which means that blood is pushing outward on those walls. If these walls weaken, you can run into problems with either developing swellings and thinnings or even bursting arteries. The fibrous tissue is mostly about holding the artery together, helping it resist that pressure. If you have weakening of that fibrous tissue, you can end up with what they call aneurysms, areas where a weakened part of the wall allows the softer inner tissues to bulge outward. You were saying something?
Oh, yeah, blisters.
Yeah, it's effectively a blister on a blood vessel. The inner layers can come out, and then you've got a very vulnerable spot. It's relatively easy for that to become damaged or to burst. Depending on where the artery is, that can be a problem or a massive problem. Questions on that? There is a phenomenon called aortic dissection. It's an unusual medical condition, but the aorta, the main vessel that leaves the heart, if you develop some kinds of weaknesses in the fibrous tissue there, it's actually possible for the aorta to effectively rip open down its length. Which, as far as I talked to a doctor who basically said, unless you happen to be on the operating table with your chest open already, that's fatal, because your entire blood supply is going to fall into your chest cavity. John Ritter, the actor, died of this. So, yeah.
What was the smooth muscle controlled by?
The smooth muscle is mostly controlled by the autonomic nervous system, although like most smooth muscle, it can also respond to various messages or hormones. Questions on that? Okay. So, arteries, their inner diameter, even on the largest arteries, is only a few millimeters, 2, maybe 3 millimeters across, even on the aorta. They have thick walls, so the aorta is actually, if you look at it in the body, it's maybe yay big. But the inner part is really pretty narrow. Given how much blood is going through that, you can say a couple things. One, it's under a lot of pressure, and B, it's moving very fast. Blood flowing through the aorta is going at high velocity. Then arteries split up into smaller arteries and into smaller arteries and smaller arteries, down to the point where they're about 1 millimeter across, where the outer diameter, the overall width of the vessel, is down to about 1 millimeter. At that point, you start seeing them turning into what we call arterioles. Now, like all blood vessels, what's the innermost layer of an arteriole? Endothelium. And while this endothelium does have a basal lamina, it doesn't have nearly as much elastic fiber as artery does, to the point where we don't really talk about a separate layer of elastic tissue. It's just got a regular basal lamina. What it does have outside of that is a fairly good layer of smooth muscle.
So we're not identifying the basal lamina on this?
Not specifically, only when it's distinctive. Now these the smooth muscle here in these arterioles kind of serves a different purpose than in the arteries. In the arteries, the smooth muscle is there mostly to apply pressure, to help keep the blood moving. Remember, things move from high pressure to low pressure. So we always want the arteries to be under higher pressure than the vessels downstream. Even when the heart isn't beating, we want that, even when it's in diastole. This muscle helps to apply some of that pressure to make sure that arterial blood is always moving along. In the arterioles, the function of the muscle is a little different. By this point, we've split up from a few major arteries to hundreds to thousands of arterioles. Each arteriole feeds a particular area of tissue. And so the smooth muscle on these arterioles is not so much about applying pressure, but about adjusting how much blood can go to that particular area. So if I'm a major artery and I'm feeding into a bunch of arterioles here, and you feed an area of the brain, and you feed some of the kidneys, and you go to the liver, and you go to some skeletal muscle, and so on. By having each of those arterioles constrict or dilate, tighten or loosen its smooth muscle, that can adjust where all of the blood in this artery goes to. Am I diverting more of it here, or about equal? These are sorry, brain crash. Arterioles are for adjusting blood flow, determining where the blood is going to go. So think of these more as valves. They also play a huge role in blood pressure, but we'll get to that in a little bit. Okay. So far, so good. Questions at this point? Now, so far though, all we've done is carry blood around. These vessels have walls that are too thick to allow materials to travel between blood and tissue. So far our transfer fluid is completely unable to transfer. In fact, some of these walls are so thick that they do interesting things. The smooth muscle in arterial walls has its own blood vessels. They call them vasa vassorum, vessels of vessels. They have their own blood supply that comes off of the artery. Kind of neat. Anyway, the next step down, the arterioles get smaller and smaller, and finally we get to the capillaries. This is where the circulatory system is going to do its job. Because capillaries are the vessels that are small enough and have thin enough walls to allow materials to move into or out of the vessel. The walls are thin enough for diffusion or active transport in some cases. And their drawing will look like this. Just endothelium, one cell layer, and its basal lect. So one layer of cells. Now, here's something to think about. I mentioned that since the arteries are relatively narrow, that means that blood is going to be going through these things at high velocity, right? What does that suggest about arterioles and capillaries? Doesn't it seem like it'd be even more so? And yet, it's not, and here's why. If you took all of the major arteries, say leaving your left ventricle, and put them side by side, there's one major one leaving, and then if you even took the ones it splits up into, you'd have a total area something like this. That's how much cross-sectional area that blood is flowing through. If you then went a little further down and put all the arterioles side by side, you'd have a cross-sectional area like this. Each arteriole is small, but there's a lot more of them. And if you took all the capillaries, now we're talking this kind of cross-sectional area. Huge. So if you imagined all of the capillaries together as one capillary and all the arterioles together as one arteriole, rather than getting smaller, we'd be going artery, arteriole, capillary, which suggests the opposite about the blood flow. The blood is going to be slowing down as it gets to these. Effectively, you've got a certain amount of blood, but rather than all of it having to get through here, it all gets through here. Make some sense? Think about it this way. Let's say you've got 5 liters per minute of cardiac output. If I were to get 5 liters every minute through this tube, it has to be going pretty fast to get 5 liters a minute through that. If I were to get 5 liters a minute through this tube, it doesn't have to be going fast at all. Pretty slow. Make sense? Some?
Arteries and capillaries are faster.
Capillaries are the slowest because if you added them all together, that's the most area. There's a whole lot of capillaries. The same amount of blood that's flowing through that artery is flowing through this many capillaries. So it's got a much bigger area to spread out into. So it's going to be flowing more slowly.
Dr. Red, can you give it a number that's easier for me? How you said few to 100, thousands. You said few to hundreds in arteries, and then thousands in arterioles. So then like hundreds of thousands
for capillaries? I'm not sure I could give you a number.
Okay, just
Probably at least hundreds of thousands. It wouldn't surprise me if it's in the millions. And of course, there's the wonderful statistic, you know, if you took all the arteries and veins in your body and laid them end to end, you would die. So, I like that version of it better. No, it is something like 50,000 miles of blood vessels in your body. So, once we've gone through the capillaries, blood is now going slowly and allowing materials to diffuse. So oxygen is entering our tissues, nutrients entering our tissues, we're picking up wastes and CO2. And then we have to start collecting them together into venules. Venules are pretty much capillaries with a little bit of fibrous tissue. A little bit bigger. Don't really do anything. Kind of boring.
And now we're heading back to the
Now we're on our way back to the heart. Yeah. And then finally, veins. Which, when you get into the large veins, end up looking kind of like this. Veins have the same 4 layers in their walls that arteries do. They have an endothelium, some extra basal lamina that's considered elastic tissue, some smooth muscle, and some fibrous tissue. But notice the difference. They're roughly comparable in outside diameter. Veins can be a little bigger than the biggest arteries. But the inside diameter is very different. Veins are much bigger on the inside and have much thinner walls. Why do they have thinner walls?
We don't need it.
Why not?
Pressure, load.
So pressure is the interesting part here. If my left ventricle puts out 5 liters per minute, how much blood is going to be coming back to my right atrium? Yeah, it better be the same. If it's not, we're leaking blood somewhere or getting blood somewhere. So I've got a closed series of tubes. If I put 5 liters in on this side, I better get 5 liters out on that side. But the pressure, so the volume can't change, but the pressure does. If I put a lot of pressure into these arteries, that pressure is effectively used up getting material through these vessels. So when I measure pressure in the arteries, that pressure is very high. And it varies by pulse. As the ventricles squeeze, pressure goes up. As they relax, it drops, and you squeeze and it goes up. That's what you feel when you're feeling pulse. The difference between ventricular systole and ventricular diastole. When I get to the arterioles, a lot of that pressure has been lost. It's used up getting blood through the arteries. There's still some pulse pressure at this point. There's still some difference, but it's less. In the capillaries, pressure is even lower, and there's effectively no pulse anymore. The pulse pressure is virtually 0. There's really no difference. By the time I get to venules and veins, the pressure has dropped to very, very low. As you know, if you've ever taken or had your blood taken from a vein, they put a needle in there and it kind of goes through. It's not under high pressure. I've heard a couple medics say that they had a person miss and hit an artery, and that blood comes out under very high pressure. Sprays, 6 feet or so, maybe more. So, but the pressure in the veins is very, very low. So they don't need thick walls. Their walls can be thin and still not have a problem. This is also why you can't take pulse from a vein. There is no pulse in a vein. The flow is steady at that point. That difference in pressure has been exhausted. Has anybody ever worked with someone with an LVAD, LVAD? Something called a left ventricular assistive device. It's something a prosthetic that can be applied to the heart in people who've had certain kinds of heart damage, and it helps the heart pump blood. In at least some of them, it pretty much takes over. I also know of at least one version of an attempt at an artificial heart that rather than doing what most artificial hearts do, which is replicate the function of a heart, this one actually used little turbines and just propelled the blood like through a jet engine. The weird thing about that one, and with at least some LVADs, is that they don't produce a pulse. They just produce a steady flow. So in somebody who's had one of these put in, you feel for a pulse, and you won't find one. It's just steady flow. They're obviously alive, they're doing fine, and their heart is working, well, sort of. But they have no pulse. And I believe that some people with these have to have one of those medical bracelets so that if they're ever incapacitated, and the paramedics come up and say, oh God, he's got no pulse. It's like, wait, before you start pushing on the chest, remember A, there's a prosthetic device in there, and B, they may still be fine. Check for a heartbeat some other way. Check for blood flow other ways. Don't just assume that there's a problem. Kind of an interesting thing. If I remember, that artificial heart also, rather than listening for a heartbeat and hearing, what you hear was from the turbines. Weirdness.
They should put in some sort of sound with them.
Why?
That way, I mean, you were like, you check for heart, like blood flow some other way, and like as an EMT, I'm like, don't teach us any of them.
I assume you could like check for like capillary fill or something like that.
You could check for that, but I mean,
Unless they have damage to their arm.
True.
they
Just don't assume they're dead if you don't find a pulse if they have one of these things.
based on very clear criteria for what a dead person is, and they don't tell you to check for that first.
Yeah, it's a rare thing. These are not common devices, but they do exist.
Maybe that's why we can't pronounce people dead.
Yeah.
Yeah.
You may have said, I apologize, so the inner diameter is bigger, and you gave us, 2 millimeter, or, 2 millimeters.
2-3 millimeters for an artery.
Right.
More like 6-8.
For the vein.
Yeah. And the biggest veins are pretty good sized, and a lot of that is internal space. Okay, any other questions on these?
You said the outside of the vein is comparable to artery.
The external size is comparable or larger than the largest artery. The biggest veins are a little bigger than the biggest arteries. At least this is, I've never actually worked directly with them, but this is what I understand. Not off the top of my head. I was guessing there, I'd guess probably 8 millimeters or so. But on the, for internal, that could be off by plus or minus 4, I'd say. I don't really know.
It's not gonna be important.
No. There's a reason I don't teach anatomy. Okay. Yeah.
For all of them that have the endothelium is all basal lamina, right?
Yes, the endothelium always has a basal lamina, and all of them have endothelium. It's just that that basal lamina in arteries and veins is thickened and has extra elastic tissue. Now that does mean that venous walls are weaker and have a tendency to stretch a little. And there's also very little way to apply pressure. There's not much muscle in the walls of the veins. They can squeeze a little bit, but we have this slight problem with pressure that in the veins, there's not really enough pressure to move the blood against the flow of against gravity. So when there's blood in your feet that needs to get back to your heart, there's not enough pressure left to push it uphill that far. So what we end up having to do in veins, especially ones in the lower body, the veins have their own valves. Periodic one-way valves in the veins going toward the heart. So that means if you get blood past one valve and then it tries to fall back, it can't. So then the next time you can get it up past the next valve. The question then is, how do you get the blood to move? Most veins lie near skeletal muscles. So that when the muscles contract and bulge, they push inward on the veins, squeezing it and helping the blood to move along.
What was the inside of the vein called, those two?
These were just one-way valves. Many veins, but not all, have these. In the video of the cardiac surgery we'll be seeing, not tonight, but later, people have been really, really wanting to see that video. People come to my office like, are we seeing the video tonight? They do a bypass by taking out something called the saphenous vein from the leg and then using that for bypass vessels. And at one point you'll notice that they take it and they check it. They push some fluid through to make sure the fluid flows, because it's not unknown to put the vein in backwards so the one-way valves are going the wrong way. So the blood from the heart cannot get to the coronary arteries that it's meant to, and then they have to go back in and take it out and flip it around. So they try to make sure that they put it in the right way so that blood does go from heart to coronary artery. Yeah. Worth double checking. All right. So now, forget all those other ones. Let's talk about capillaries. They're the really interesting ones anyway. These are the vessels where stuff can actually cross. So these are really, physiologically, probably the most important vessels. They are very small. They're microscopic. Generally, these are about 6 to 8 microns in diameter. I'm going to expand that range a little bit. 5 to 10. Remember, a micron is 1,000th of a millimeter. So you could generally fit something like 100 to 200 of these side by side in 1 millimeter. They are smaller than we can see with the naked eye. Also, given that red blood cells are about 6 to 8 microns across, if you were to take a capillary and look at it in side view, here's the cells that form its wall. There's the endothelium. A red blood cell, generally about that big. Red blood cells go through these things in single file. White blood cells, as a rule, don't go through these. There are non-capillary vessels that bypass capillary beds that help white blood cells get through. Most white blood cells can't easily fit through capillaries, they're too big. Yeah.
Are there walls of all of these areas, like the endothelium of all of these areas, releasing prostacyclin?
For the capillaries, at least on typical capillaries, yes. The endothelium turns out is not as passive as we thought. It is actively interacting with the blood, and prostacyclins are one way it does that.
Okay.
Now there's a couple types of capillaries I'm not sure about, but we'll get to that. So, most capillaries in your body are of a type we call continuous capillaries. Which means that the wall is unbroken. The capillaries form a solid layer, which means stuff can't get through except where the endothelial cells join together, the junction isn't quite perfect in most capillaries. Where these two cells join together, we have what's called a leaky junction.
Inside the continuous capillary.
Yeah, this is for in the walls of continuous capillaries. Where the endothelial cells come up together, they form what's called a leaky junction. And it's barely leaky. That's a very, very narrow gap. The gap is generally too small for things like glucose to get through. It's just big enough to allow water and ions to pass through. Which means your capillaries can allow water and ions to go out or in from the blood. Not just that, but they can't directly control that. We're going to take a moment here to talk about what kinds of things can cross capillary walls and how. So for a continuous capillary, water, ions, and gases can cross freely into or out of the blood vessel. Remember, gases can cross cell membranes. So oxygen and CO2 can go right through those endothelial cells. Water and ions can't, unless there are channels for them. But they can pass through the leaky junctions. Organic small molecules like glucose and amino acids the endothelial cells can have carriers for those, so that they can pass through this wall if the cell has carriers on both the inner and outer membranes. That means these cells can decide which kind of small organic molecules can get through.
So they can pass if there are carriers.
If the cell allows them to pass, yeah. Proteins generally don't. In the cases where the cell needs to bring in proteins or export proteins across that wall, there are active transport mechanisms for doing that. Mostly, if you remember from basic bio, endo and exocytosis, that's usually the way it goes. Briefly, if I've got a protein here that needs to get through this cell, what'll happen is the cell will use endocytosis to bring the protein in, seal it up in a bubble, move the bubble through the cell, and release the protein on the other side. I guess we could simulate this, although we won't. We could have everybody standing hand in hand to form a membrane, and somebody be a protein. So they come up, and people just go, and then join hands, and now we've made a little bubble inside, and we shuffle them over, and then we join with the other side, and let them out. We probably don't need to go through all of that.
Dr. Rad,
Yes?
on the
continuous capillaries, the
Go ahead.
circle is the endothelium.
Yeah, these are the endothelial cells. They're very thin, flat cells.
So were the leaky junctions, okay, I guess that picture's confusing me, the second one.
This is just a close-up view of where these two
Oh, okay, I get
endothelial
it.
cells come together.
I get it.
Make sense?
Yeah.
Most of the capillaries in your body are this type. There's a variation on these that you find in the central nervous system, where glial cells called astrocytes add an additional barrier. So in addition to our endothelial cells, other cells called astrocytes also envelop the blood vessel, adding another layer that things have to pass through. It tightens it up a great deal. Very few things pass in and out of these capillaries in the central nervous system except gases, some water, and strictly controlled salts and small organic molecules. You may have heard of the idea of the blood-brain barrier, which refers to the concept that the body exerts a great deal of control over what sorts of things from the blood can enter the brain. This is pretty much why. So between the endothelial cells and the astrocytes, only things that are allowed through by these cells can get through. As an example, Parkinson's disease is caused by a lack of the neurotransmitter dopamine in an area in the midbrain. People tried to treat this by giving people dopamine, but it didn't work because dopamine doesn't cross the blood-brain barrier. One of its precursors, levodopa, does. So early Parkinson's can be treated with levodopa, which is then taken up by the midbrain and turned into